Page 226, number 7. Ha, fooled you. You thought I was going to do number 8. And number 7 is even one of your homework problems. We're going to do it together. And here's why. This is a critically important type problem. It's a very common calculus problem. You know, it just shows up on tests, you know, in any course that you do on the AP exam and in books. It's just like a classic problem, and it is also related to your project. Your project is going to be really based around number 18. So make sure you watch the video for number 18. You know, apart from that, once you get the idea of these, you can, you know, stop watching the videos and just, you know, get to work on the homework. But do, you know, have a close look at number 18 and see if we can figure out, look ahead, see which video that is, and make sure you watch that one. All right, and also this one, number 7, optimal dimensions. What are you doing here? You are planning to make an open rectangular box from an 8 by 15 inch piece of cardboard by cutting congruent squares from the corners and folding up the sides. What? What are the dimensions of the box of largest volume you can make this way, and what is its volume? What are they talking about? Well, I will tell you. You have a piece of paper, like this one, all right? And what you're gonna do, I'm gonna zoom up. I guess that's as far as I can go. All right, I have this piece of paper. And let's pretend that this piece of paper is 8 by 15. So, okay, it's 8 centimeters up here, and it's 15 here. It isn't really, but let's pretend. Now, what we're gonna do is we're gonna cut congruent squares. All right, what does that mean? I'm going to cut a square here. It's going to be x by x because it's a square. And I'm going to cut congruent squares off of each side of the box, all right, of this piece of paper. Off of every corner, I'm going to cut off x by x, and the x that I'm measuring is going to be the same every time. That is an exact precise measurement at an exact 90-degree angle, as you can clearly see I've done. Okay? And then what you're going to do is you're going to cut out the corners. So I'm going to cut out the corners. We're going to here, cut this out. You're going to make one of these. Actually, yours is going to be slightly more complicated. So if you want to look ahead at number 18, you'll see why. Cutting out my congruent squares. Of course, when you make yours, you're going to measure everything exactly and use, you know, rulers and protractors and such things as that. If you don't have a protractor, you can just use a square corner of paper to make a right angle. We'll pretend that I cut right on the lines, and it's all good. You can tell, like, I got a 0 in arts and crafts. Okay, so now I've got this shape, right? So now what I'm going to do is I'm going to fold up the sides. Fold up the sides. There, see? I got a nice box. It's an open top box. All right? It's a nice little box. Put some cat litter in there. The cats use it for cat box. Or they could just play in it. Don't put cat litter in it. They could just jump in there and hang out because they love that kind of thing. All right, that's how you make the box. Now, how am I going to solve the problem of, like, I just arbitrarily decided to cut off this much, right? What if I cut off more? It's going to make the box taller, but also skinnier. So what is the optimal amount of x to cut off to make sure that this box has the maximum volume? And that's, you know, a reasonable thing because it's how we make boxes. We're going to have some flat thing and fold it up. All right, so we need to get an equation that expresses what we're trying to maximize. Right, that's our step 1. So we know for a box, volume is length times width times height. All right, and then on our box. There's our box. Okay, maybe I can see the back a little bit. I don't know. All right. Anyway, height, width, length. So volume is height times width times length. Okay, but how does that relate to my only variable, which is x? Well, I can see that when I folded up the box, the height of the box is going to be the x that I cut out, right? That's going to make the height of the box. So the height is x. Now, what about the length and width? So this box was 8 centimeters wide before I cut off the 2 pieces. Now each piece was of length x. So I had, if I draw this out here like this, right? So this distance was 8, but I cut off x from every corner. So how long is the actual bottom of the box? How long is that going to be? It's not going to be 8 because I cut off x from each side. It's going to be 8 minus, take away an x from this side, take away x from this side, 8 minus 2x. So that's going to be the length. It doesn't matter which I call the length and which I call the width. Length is 8 minus 2x. So then what about the width? This thing was originally 15 centimeters wide, right? It was originally 15, but that was all the way across before I cut the corners out. So once I cut those corners out of x on each side, I have 15, take away x, so that width is going to be 15 minus 2x. All right, so that is step one in setting up this problem, is to understand how the folded paper makes the box, and then how the x in the box makes all of the dimensions of the paper. So the next thing that we want to observe on this is there is a hidden interval for x, because we know that all of these dimensions have to be positive. And this is going to come into play in your project also. So this means that 8 minus 2x has to be positive, and 15 minus 2x has to be positive. So this means that 2x has to be greater than 8 and x has to be greater than 4. This means that 2x has to be greater than 15 and x has to be greater than 7.5. Well, if x is greater than 4, it's automatically going to be 7.5. So this one determines the interval. Now we also know that the x is positive, x is greater than 0. So x is between 0 and 4. So by really looking at these dimensions and the fact that they have to be positive, we excavate the hidden interval that x has to be in the interval 0 to 4, not including the endpoints, because none of these dimensions can be equal to 0. If x were equal to 0, then I didn't cut off anything and I don't have a box. If x was equal to 4, I would have cut 4 this way and 4 this way, and I've cut all of the box off and there's nothing left to fold up. Okay, so this is an open interval from 0 to 4. So now I'm solving this maximum value problem on an open interval 0 to 4, and that's what we will look at next.